Hello everyone. Welcome to today's Fundamentals and Application of Outdoor Reset webinar, a 1-hour, 1 PDH credited presentation. My name is Miranda Gettling, and I'm the Academy Manager here at Viessmann. I just wanted to say thank you for attending today. Despite what we're all going through, we appreciate you still attending this webinar. Today, your webinar instructor will be Jody Samuell. Jody is a graduate of Maine Maritime Academy with a degree in marine engineering. Over the past 20 plus years, he has worked with various companies, including Amtrol, Viessmann, and Caleffi, serving in various roles, including application engineer, product manager, training manager, and manager for engineering education. Currently, he serves as a project development manager for Viessmann. Before we begin, just a few housekeeping items. As I stated in the beginning, this is a 1 PDH credited presentation. If you indicated upon registration that you would like to receive this credit, the RCP provider has a mandated survey that needs to be completed, which I will email out to you at the end of this webinar. If you don't need the PDH credit, we still ask that you fill out the survey to help us further improve our webinars. Once we've submitted the PDH credit, due to the current situation, we will be emailing out a PDF version of the certificate within about 5 business days, rather than mailing it out like we normally would. If you would like us to mail out a hard copy to you, just let me know and we'll make sure to do that as soon as possible. Everyone will stay muted throughout the webinar. However, at the bottom of your screen, you should see a Q&A button. On the left, you will see the desktop laptop version, and on the right is the mobile device version. Jody will be stopping about halfway through the presentation as well as at the end, so if you have any questions, just pop them in there and he will answer them. A recorded version of this webinar will be posted in the next few weeks on the video library. This will be located on the same website you went to register for this webinar. Once you are in that video library, you will have to click this recorded webinar section and then the Discover More button at the bottom. There are quite a few webinars in there right now, so you may have to click that button more than once. With that being said, let's begin. Here is Jody Samuell.
All right, I think we're all set to go. So as Miranda said, thank you for all for coming today. And today we're going to talk about outdoor reset. And this actually was a presentation put together for this time of period. But as a topic, it's one that comes up a lot of times when discussing other topics or phone calls with individuals. So there's a lot behind what we're going to talk about today. Now let's roll through some of the housekeeping slides. So as Miranda said, this is a credit for PDH. This is the group we're affiliated when we do our PDHs. The presentation is copyrighted. If you'd like a copy of it, let Miranda know on the survey. We can give you a PDF of it. And going to jump through the purpose and kind of get down to the learning objectives. And for a lot of people, for a lot of times, everybody looks at outdoor reset as something we all do, but we really don't talk much about. So this is really kind of the behind the scenes discussion on it. So we're going to explain the heat flow process from the burner to outdoors and how the outdoor reset can control it. And that's really what we're talking about, is controlling the heat flow process. We'll list the benefits of outdoor reset. There must be a reason for doing it. We'll explain how outdoor reset works, and then we'll describe the process of selecting a heating curve for an application. And you'll find we'll talk about a number of different topics along the way as well to frame this out. And it will be a good solid hour. But again, as Miranda said, if you have questions, please type them in and we'll cover them at a couple points along the way. Now we talk about outdoor reset. It's really all about controlling a heat flow process. So if I look at a building, whether it's residential or commercial, we're really trying to control what I have on here. So on one end of the process, I have combustion going on inside my boiler. On the other side of the process, I have the outside air, the air surrounding the building. And what happens is, in order to keep, and when we do this, our real goal is right here, maintaining temperature in the building living space. But what we're really trying to do is really trying to control essentially three heat transfer processes. Because I'm going to burn my fuel. That fuel, those combustion gases will pass through a heat exchanger. So here's one heat exchange process going into the hydronic water. That water then gets pumped to a different area within the building where it's going to be passed through some sort of a heat emitter. And then this heat emitter, the water going through the heat emitter is going to transfer its heat into the air that's going to end up in the the living space. It may be the heat emitter is in the living space. It may be that the heat emitter is in the ductwork somewhere and that gets forced into the living space. But again, another level of heat transfer. And then finally, the one that we don't control is the living space losing energy to the outside air temperature, the outside world. Yeah. So when we start to build and design, there's always going to be some set points in here. And then it's a matter of how are the other points responding, or what do we have to deal with when we look at some of the other points as well. But our goal in this entire process is I want each one of these 3 heat transfer processes to be balanced. I want to put the right amount of heat into the hydronic water, to put the heat into the living space to compensate for the heat that the living space is losing from the outside. Now, a couple of set temperatures, okay? In this process, we're not controlling the combustion gas temperature. If I did methane with 0 excess air, about 3,500, in most cases, it's probably going to be about 300 degrees. So that's not controlled in the process. Usually, the building living space is what's going to be specified. So when we design the heating system, we're going to talk a little bit about heat loss. That has to be defined for us. Good round number, 70 degrees. It might be 68, it could be high as 72, but generally that's a number that we're going to be given with to work with. And then it's a matter of, from a design standpoint, where does the water temperature need to be? That's important for heating the building. It's also important for setting up the control to heat the building. And also, what's happening outside the building? What's the outside temperature going to be? But when we start to look at these processes, it's really all about defining this and then defining that. And then once I've defined those two, then I can start looking at how I'm going to control it. Okay. Now, from a process standpoint, I'm not going to start here and work out. It's really about starting here at the heat loss of the building and then work my way back to where I need to be. So let's talk a little bit about heat loss. Okay. From an aspect of heat loss, we have to know something about this, because the reality is every building out there, every application is not created equal. Yes, heat moves from a warm place to a cold place. That's a given. Inside the building is going to be warmer than the outside, and that's going to drive the heat from inside the building to outside. And our goal is to replenish that heat to maintain a consistent temperature inside the building. And from a design standpoint, the heat moves faster when there's a greater delta T, a greater differential temperature from inside the building to outside the building. Okay. Now, when we start to look at designs, then all of a sudden the location or the climate comes into play, as well as building design. Because I can have 2 buildings exactly alike, same square footage. I put one in Bangor, Maine, where the design temperature is minus 15 degrees, and I put one in LA, which the design temperature is probably somewhere around, maybe 45, 46 degrees. And what we're going to find is, although the structure is designed exactly alike, when I design a heating plant, I'm going to need more heat to go into the building in Bangor, Maine than I am in LA because of the colder temperature on the outside. Additionally, when we look at this, we also have to look at the building construction. If I take 2 buildings and I happen to be outside of Providence, Rhode Island, I look at 2 buildings in Providence, exact same square footage. If one is built in 1920 and one was built in 2010, the 2010 building is probably going to be better insulated and better designed than the building that was from 1920. And for the same square footage, I am going to need more heat into the building to make up for the heat loss in that older building. So we start to look at the requirements of heat in the building. There's not a set number. And that's one of the ones that I always run across as somebody says, okay, can you give me a number to work with to size the heat emitters in the building? And they're expecting me to say, well, why don't you just use 35 BTUs per square foot or 25 BTUs per square foot or a certain number? And my answer always is, it depends on a lot of things. It depends where you are, excuse me, and it depends on the building construction method. But all of this plays into the heat loss. So we look at that heat loss, we look at it from the aspect of, we have to make sure the building is heated on the design day. So on that design day, we're going to define the inside temperature, and then we need to establish an outside temperature, because that temperature difference or gradient is what drives the heat loss. Now here I have 0 degrees. I picked that number based on ASHRAE weather data. And if you're wondering what city I'm looking at here, I'm going to go with Boston, Massachusetts. 0 degrees in Boston is going to give me 99.8% coverage. I like to cover as much as I can. You know, some people will design at 100, some at 99.8, some of it maybe at 99%. But you define the outside temperature, because once I establish my outside temperature, the temperature gradient from inside to outside is what drives the heat transfer, okay? So on a 70-degree inside temperature on a 0-degree day, that defines the heat transfer. That's 70 degrees of delta T, which goes into the heat loss of the building. Additionally, when we start to do heat losses, the other thing that always comes into play also is wind. You know, standard's probably either a 20 or 25 mile an hour wind blowing on all 4 sides of the building. That plays into the heat loss as well. So from a design standpoint, then it becomes, how do I do that heat loss? Okay. If I'm old school, it's a piece of paper. So this happens to be the old IBR calculation sheet. You know, start with IBR. You also start with the Hydronics Institute, where everything went electronic. You know, so here's one, and it's simply a room by room heat loss, looking at the dimensions of each individual room, and then the factors for each one of those design pieces. And the goal is to come up with the number of BTUs for each individual room, of which I will eventually add up. You say, okay, for this building, I need 50,000 BTUs. Now that 50,000 BTUs is important because I can then use that in sizing my heat emitters and also selecting a water temperature, one of my other key things I need. That's old school. This is how I was doing heat losses probably about 12 years ago. This is Soft's product called Right Suite. It has all the same information. So up here is all about the building structure. You know, what is the construction method for that building? Then down here, rather than filling out a table for dimensions, you simply drag and stretch a room out, add in windows, add in doors, and all the work is done. But if done properly, you'll find that no matter which method I'm using, you'll find the heat loss is pretty close to each other. Another nice thing about something like this is if you look down here in the HVA shapes, this squiggly line, this program also allows me, if I'm doing radiant, to put radiant in the room. And by putting radiant in the room, I can define, you know, tube diameters, tube spacing, material construction, and this program also will give me a water temperature, which ultimately is one of the things I need to know. So I do my calculations. I have my outside temperature. I have my inside temperature. I have pulled up my outdoor air temperature based on the ASHRAE data that I used in doing my heat program. I've calculated how much heat is needed here. So if it's balanced, if I'm losing 50,000 BTUs, for instance, here, that means I have to have enough heat emitter to put 50,000 back into the room, which will lead me to my temperature here. So let's look at heat emitters. Okay, so I'm going to look at it from the aspect of, you know, some of the standards, baseboard and air handlers. I just left radiant as a note off to the side here. When I start to pick the water temperature, if I'm doing radiant, it's going to come from the software package that's utilized to design the radiant system. So it's going to tell you that I need, you know, 8 gallons a minute for this building at 110 degrees Fahrenheit. So it's nice in that fashion that that number comes at you. But when it comes to doing baseboard, in the world of baseboard, I have to select my water temperature. So this is a typical chart from a baseboard manufacturer, and I can size baseboard anywhere with 110 degree water up to 220 degree water. I'm going to look at 2 individual spots along here. So the old standard is sizing at 180. With 180 degrees, everyone will say, yeah, I do 180. I know the baseboard is going to be at about 600 BTUs per linear foot. This manufacturer is 610. So if I was using this baseboard for that application for 50,000 BTUs, I could do it with 180 degree water, with 610 BTUs per linear foot at 4 gallons a minute. I would need about 82 feet of baseboard to adequately heat that building. I have the option of changing though. I don't have to go at 180. I could also do it at 150. Lower water temperature, baseboard puts out less BTUs per linear foot. Now that 82 feet of baseboard goes up to now 125. Okay. My other option is doing it with an air handler. So here's an air handler. I can size at 120, 140, or 180. I know that I need 50,000 BTUs. So here's 140. Here's 2 gallons a minute. Low fan speed, there's 50.4. So there's my 50,000 BTUs. So when I look at this, I have 2 options available to heat the building. I can do it here with this water temperature, or I could do it anywhere along here. Let's say I could do it at 180 with 82 feet of baseboard. I can do it 150 with 125. For our discussion, I'm going to go standard. I'm going to say, you know what? Based on all of these, and based on the fact that I only feel like putting in 82 feet of baseboard, it's going to save me money, I'm going to go with 180 degrees. Yeah. From an efficiency standpoint, yes, I will pay for it on the backside, but we'll go through that for the discussion point. Okay. So when I start to look at the heat emitters, and a lot of times when we get to existing buildings, we're putting in a boiler with outdoor reset. The question always is, where should the water temperatures be? Yeah. So if I'm doing baseboard, it's probably, and it's existing, it's probably somewhere in this area here. And most likely it's probably going to be somewhere between 180 to 190 degrees. Fan coil units, they may be sized anywhere from 140 to 180. Again, in most cases, it's probably going to be somewhere in that 170 to 180 range. And you can go down through here. There's a lot of things that are considered high temperatures, medium temperatures, for instance, low mass radiant or cast iron radiators, or low temperature systems like radiant floors where I'm down around 80 to 120. But from an aspect of choosing the water temperature, there is a wide variety of water temperatures that potentially could be utilized to heat a building. So it's really, I have to know something about the boiler. What's the heat emitter? What's the design heat load? And what was calculated for it? Because there is a wide variety. And a lot of times people say, well, what do I use? And it's well, I really don't want to guess. Let's talk about what you have. So let's look at what we have here. So we decided on a 70-degree room temperature. There's my combustion flame temperature. Based on the ASHRAE data for the location, we have 0 degrees. We've calculated the heat loss here, and we've decided to balance the heat load here using 82 feet of baseboard. I need 180 degree water. So from an aspect of design, and I talk in an aspect of doing outdoor reset, I now have 2 pieces of information that I need to set my control up. I have here the information for my design day. And it doesn't matter the control that you're utilizing, whether it's ours or somebody else's, you have to define the design day to program it. 0 degree day, 180 degree water. Now then after that, it now becomes a matter of how do I get a curve from there, or a reset ratio. Now, if I look at performance of the building, this is what I'm designing for. So you notice here, I've shifted over to 7 degrees Fahrenheit. That's the 99% number. I am over here at 0 degrees from what I did. I'm looking for 99.8%. Now, if you look at the time that's spent out here, we have to design for the coldest day of the year because we do not want to complain about the house not heating when it gets to 0 degrees outside. But if you look at the hours of operation, and again, this is for Boston, you spend the bulk of the time pretty far away from the time period that you're designing for. Okay. Now, with that temperature, without outdoor reset, let's say I'm looking at a 35 degree day, right in this column right here. On this point here, if I still operate under these conditions, I am providing enough heat in the building to heat the building under design conditions, but from an aspect of performance, I'm nowhere near that. So let's talk about that, okay? So on the design day, I have my inside temperature, my outside temperature, I have heat loss. And that temperature driving across here, that 70 degree temperature drives that heat load. Let's call it my 50,000 BTUs. that we talked about earlier. Now, this whole balance changes when the outside temperature changes. Let's say I'm not on the design day. Let's say it's a 35-degree day. Now, all of a sudden, this 70-degree delta T doesn't exist. If I'm 70 degrees inside the building and 35 degrees outside, I only have a 35-degree delta T. The driver for that heat across there is halved. So if I have half the delta T, I have half the heat escaping from the building. So all of a sudden, on the 70-degree day, I'm losing 50,000 BTUs through that wall. On the 35-degree day, I'm only losing about 25,000. So because I want my 3 heat transfer processes to balance, heat loss through the wall, heat transmission out of the heat emitter, heat transfer across the heat exchanger in the boiler, because I want those 3 to balance, all of a sudden I have to find a way to balance the other 2 heat transfers when this one shifts, when the outside temperature changes. And now we're getting into how do I control that system when I am pushed away from that design day that lasts a very short period of time, okay? And really, how do we maintain comfort? You know, this isn't, when you look at buildings, it's not an engineering exercise to figure out heat transfer. Ultimately, it's the temperature in the building is one of the factors in comfort. So how do we, from a temperature standpoint, contribute to the comfort in that building? Okay. Yeah. So if we're looking at balancing that room temperature, it becomes how do I balance the amount of heat that's being transferred in through my heat emitters into that building? And there's a few different approaches to getting there. The first one, I'm going to call it pulsing. Do I pulse the building? Pulsing the building is really the most simple. So when I pulse the building, everything stays the same. I run under the conditions that are needed for the design day, but now I'm looking at it from the aspect of reducing the heat loss of the building. So I've half the heat loss, so I have half the heat loss passing through here, which means when I look at what's happening here, I have to drop that in half as well, okay? So from an aspect of pulsing the building, I maintain the same water temperature, I maintain the same design flow rate of that water, but then I bring the thermostat into the picture, I bring zoning in, either zone valves or zone pumps, and I utilize that thermostat in the living space to pulse the building with design heat, 50,000 BTUs per hour, in chunks of time, so that I'm now balancing against the 25,000 that I'm only losing. So basically, the boiler, the pump, stay on for about 50% of the time. So it comes on for 3 minutes, maybe 4 minutes. It turns off. The temperature in the room drops, the thermostat calls it back on again, and I pulse the building again, okay? Now, the thing with this pulsing of the building, I don't do anything from an aspect of water temperature. And I also start to build into what's called cycling losses, okay? So I'm maintaining the boiler temperature hot. So whether I'm on the design day or the 35-degree day, I get 180-degree boiler water temperature. It's simple from a control aspect. The boiler's always running hot, okay? But if I look at it from a cycling loss, and this happens to be a chart I found on cycling losses, the blue line represents a conventional boiler or a traditional boiler, and the bottom axis is percent of power loss, the vertical is the efficiency. So here it's going to near condensing, it's about 87%. So if I'm running at 50% load due to the cycling losses, I'm down to about a 75% efficiency. If I'm running at 30% load, I'm at about 57, 58% efficient. So one of the downsides of pulsing the building is without a modulating burner helps a lot from this aspect, but particularly if I'm doing a single stage burner, like, the markets that are still doing oil, a lot of the Northeast still does it. As the load drops, the efficiency drops because of this cycling of the system. Now, the other thing that comes into play, you might look at this and say, well, at 50%, I've only dropped from 87 down to 75. My question always is, was your boiler size exact for the load, or is it oversized? Because that boiler's oversized 25, 30, 35, 50%. If I'm oversized 30%, all of a sudden, this is not coldest day of the year. Coldest day of the year happens somewhere around here. So I've lost efficiency out of the gate. And then when I'm at 50% of load, I'm pushing more closer to 60% efficiency. At 30% of load, I'm pushing closer to about 45% efficiency. So when we start to look at doing outdoor reset, one of the key things is by doing outdoor reset, it can help us address a lot of the cycling load by bringing those temperatures down. Okay. Now, the one thing that we do have to work against when I start to look at doing outdoor reset is when I do a conventional boiler, I do have to pay attention to where that dew point is to stay above it, because I do not want that boiler to condense. Now, if I'm doing a condensing boiler, and that's why I have a star down here, the other thing that I have to pay attention to is if efficiency is part of the equation, I may have to be at this temperature here on the design day to make sure that the building adequately heats, but I want to spend as much time down below this dew point to get the boiler to condense so I can maximize the efficiency and the performance of the boiler. So a lot of times when we start to look at doing this pulsing of the building, the non-outdoor reset application, because of cycling losses and because it becomes difficult with an existing building, strictly maintaining a single temperature to drive the water temperature down as low as possible to get the boiler to condense, it a lot of times doesn't make sense to do it. There's savings associated with it. So our next approach then is, can I change the heat output of the emitter? Is there a way to drop that? And from the emitter standpoint, it's receiving a set flow rate and it's receiving a set water temperature. What happens if I adjust the flow rate? Let's take a look at that. Now, easiest way to do it, rather than throwing up equations, is to look at the output of a heat emitter. So we'll look at a couple of these. So here is the heat output of baseboard, and you'll notice it's sized at 4 gallons a minute and it's sized at 1 gallon per minute. Let's go back to our 180-degree water going to the baseboard. At 4 gallons a minute, I get 610 BTUs per linear foot. If I drop the flow rate down to 1 gallon per minute, it only drops down to 580. 580 represents about 95% of that 610 BTUs per linear foot. So I've dramatically dropped the flow rate, but I've marginally dropped the output. So I don't get good response as far as balancing the system on water flow rate alone. Drop it to a quarter, still getting 95% of the heat out. Now, the other thing to consider, and this is more for loop systems where I have series loop emitters, is if I'm sizing at 4 gallons a minute, if you work the numbers for 610 BTUs per linear foot at 4 gallons a minute, the drop per foot is about 0.3 degrees Fahrenheit per linear foot. If I slow the water down to 1 gallon per minute, how I still get all of that heat out is my temperature drops more dramatic. It increases from 0.3 degrees Fahrenheit to 1.16 degrees Fahrenheit, almost a quadrupling. So from a standpoint of series loop systems, this always becomes the big possible issue if somebody says, let me slow the water down. At 4 gallons a minute, it's very easy to keep the delta T close to maybe a 20-degree delta T, keeping the performance at both ends of the run of baseboard pretty close together, but I slow it down and all of a sudden I see a dramatic change in how much BTUs per hour are coming out of that last foot of baseboard versus the first. I start to see an imbalance in the room temperatures in the building if they're in series. So we start to do adjustment with flow. The things that we see, as you see here, I don't see a good proportional drop in temperature for a drop in flow rate, a good proportional drop in output for a drop in flow rate, but I do see an excessive drop in temperature, which I may not control. Same thing happens when I do air handlers. So if I do this air handler, look at sizing it at 6 gallons a minute at 180 degrees, I have about 100,000 BTUs coming out of that heat emitter. If I drop my flow rate down to 2 gallons a minute, leave the fan still at that low speed, I'm down to 79,000 BTUs. So I've dropped the flow rate by a third. I'm still maintaining 79% of the output. And you will see the delta T has probably come close to tripling, very close to tripling by dropping to the lower flow rate. You know, from an aspect of condensing boilers, you know, by dropping that flow rate, you know, that's never a bad thing because it's going to drop my return water temperature. But if I'm trying to slow the flow down as the method of controlling the amount of heat that's going into the system, I don't have a good response from that side of things. So when we look at flow rate, you know, adjusting flow rate's never bad, but it doesn't provide proper regulation of the heat output by itself. Okay. So the other thing we can look at is changing water temperature. Now we're into the world of outdoor reset control. So if I change the water temperature, as you see here with this baseboard, as I drop the temperature, the BTUs drop. So if I said, you know what, at 180 degrees, I need 610 BTUs per linear foot on the design day. On a 35-degree day, I need to cut that in half. So if I look along here, and I say, okay, 610, halfway of that is 305. Well, here's 270, here's 340, that's 130, that's 140. That's telling me that if I drop my low water temperature from 180 to 135, I reduce the heat output in half. So I start to do outdoor reset. It's all about measuring the outside temperature, measuring the water temperature, and then making that temperature change. And as I make that temperature change, the amount of heat emissions out of the heat emitter reduce, and by reducing that, I can maintain consistent temperature inside the building. So it's all about making that adjustment. You know, whether it's, you know, baseboard, it's radiant, or it's convectors. I mean, it's air handlers. Now, one thing you'll notice here, and I like to point this out because you do run across this when you're doing baseboard, you'll notice here the chart stops at 110 degrees. Okay, and why it stops at 110 is the heat that's being moved into that room. The room is actually, the entire volume of the room is heating through convection. I'm setting up convection current inside that room. So if you look here, here's my baseboard. Air enters in the bottom, passes across the heat emitter, and then exits through the dampered area here. And when it exits, what I'm trying to do is I set up a warm air column on one wall of the room, thinking of it very similar to setting up draft in a category 1 chimney. I want to have a lower density, warmer air, causing it to rise up on one section. And then by that moving in that direction, it starts a convection and turns the air over in the room around slowly, providing for heat all the way through that room without having to force the convection with a fan. Okay. Now, why most of the charts stop is the driver here really is a difference between the water temperature on this coming into this pipe into the heat emitter and the outside air temperature. Eventually, the temperatures get so close together that I don't generate enough temperature here to cause this to happen. You know, just as when with sizing a chimney, you get to a point where, you know, your flue gas temperature may not be high enough to draft the chimney. The same thing happens here. My temperature coming out of the baseboard for the air is not enough to cause that convection to happen. And that's why, you know, when you look at things like baseboard, a lot of times when we do outdoor reset, there's a minimum water temperature that's associated with it. Yeah. Fan coil units, as you can see here, as I drop the temperature down from 180 to 140 to 120, yeah, there's a consistent drop across there, allowing me to work with this and control the amount of heat going into the living space to help maintain a consistent temperature. And it, you know, so when we start to look at outdoor reset, there's a lot of things I can do with it from a temperature standpoint to improve the performance and the comfort in that building. Okay. So when we look at that heat flow standard, I look at combustion temperature, I maintain the living space. The outside temperature varies. As the outside temperature varies, the heat loss here varies. And what we're trying to do is and ideally we would do constant circulation where a thermostat won't come into play. But ideally I will vary the water temperature here. And by changing that water temperature here, I will maintain the temperature there. Okay. So on the design day, it's 180-degree water, it's 0 degrees on the outside. For this example, on a 35-degree day, it's 135-degree water, and in both cases, the room temperature stays at 70 degrees. Okay. Now I made a quick look, and it appears there's no questions yet, so we'll continue to move forward. Okay. Now, the other thing that happens, and we'll kind of summarize at the end to talk about all the benefits, but the other big advantage here, not just about a comfort standpoint, but there's also an efficiency increase as well. Because if I've reduced the delta T here, if I've reduced my water temperature, as the water temperature goes down, the return water temperature goes down as well, and I'm also going to have better heat transfer. So we approach here, it's good from an aspect of comfort, but it's also good from an aspect of efficiency on the boiler side. Okay. So outdoor reset, why does it work? Well, the first thing is we can measure outside temperature very easily. And by looking at outside temperature, it gives us a guide to the heat loss of the building. I put the sensor out there. When the outside temperature gets colder, I know that I have to increase my water temperature, and by increasing the water temperature, I increase the heat that's going into the building, and I keep that building constant in temperature. Conversely, I see the outdoor sensor senses the outside temperature coming down. As the temperature comes down, it increases the water temperature, increasing the heat going into the building, balancing the heat loss, again, maintaining constant temperature. But it's all about keeping that building, into balance with the outside environmental conditions. Okay. So with outdoor reset control, we're going to, on the design day, achieve design conditions, but unlike the traditional control of off-on, what we're now going to do is measure the outside temperature, and as the temperature goes up, we'll pick a point on this curve, and then we'll go to a lower water temperature. Okay. So for instance, we look at something like this. So here's a curve, a heating curve out of a manual. Now you'll hear this referred to as a heating curve, a reset ratio, or also a slope. This is going to be picked for a very specific set of conditions. Bottom is outside temperature. The vertical axis is boiler water temperature. So if I was going for a -4-degree day where I needed 140-degree water, I'm going to have a heating curve of 1.0. And then that 1.0 heating curve then defines all of the other points as the outside temperature changes. So if it's -4 outside, it's 140 degrees. If it's 23 degrees outside, it's 122 degrees. If it's 50 degrees outside, it's 95. So I'm constantly measuring, I'm constantly changing. And if this is the heating curve for your building, the temperature is going to stay at a nice consistent 68 degrees. Now, if this isn't your building, this may be your building. On that -4-degree day, I need 180-degree water. Now that heating curve is not down here at a 1.0, it now becomes a 1.6. Now my points change that on a 23-degree day, I need 158-degree water. On a 50-degree day, I need 110-degree water. But again, if it's the right curve for the existing building, this building also will maintain a consistent 68 degrees. Okay? And that really is the core of doing outdoor reset control. Okay. General rules of thumb. And a lot of times the question comes up, well, I have an existing building, I don't have a lot of data, where should I start? Generally, if somebody says they're doing high temperature, it's probably going to be, your starting point is going to be somewhere between a 1.0 to a 2.0, 1.4 to a 2.0. that's my high temperature systems, my fin tube baseboard, my fan coil units. If a medium, it's probably going to be about a 0.8 to a 1.4. Low temperature systems, maybe as low as 0.2 up to about a 0.8. And again, these are general numbers. And a lot of times, based on the amount of heat emitter that's in the building, it's not uncommon to see fin tube baseboard running at a heating curve of a 1.0 or maybe, a 1.3 or maybe a 1.2, because of the fact that you have more lineal feet of heat emitter in the building, you can drop the water temperature. But these are kind of general rules of thumb that most people will look at when it comes time to set up a heating curve for a heating system. Now, I want to put a couple of points in here. 3 points, again, to bring back that whole discussion about temperatures. Because here, being a guy from the Northeast, immediately I'm concentrating over here on the cold weather days. So the thing to remember is when I look at the application, this guide here isn't just about where it's contacting here, it's all the way across. So I look at providing for 160-degree water into a building. If I'm in Boston, Massachusetts, to get that 160-degree water, I need a heating curve of 1.3. If I'm in LA, where my design day is probably somewhere around about 45, 47 degrees, to get that same 158, 160-degree water, that's a heating curve of 2.4. If I'm somewhere in the middle, let's call it about a 20-degree day, probably somewhere down around DC, that's a 1.6. So when I look at this, remember, these numbers here, these lines do go all the way across. It's not just about here. Although, all of us that have come out of the Northeast market, this is always where we tend to focus. But I wanted to, make sure I made that point about, it being market specific about where you are in here, not just concentrating on the cold weather days. Okay. So from an operational standpoint, I have my design day here, and I left my hours up for Boston, just because I like to always give the reminder to everybody about the dispersion of temperatures. So on a design day, I provide 180-degree water. And if this is truly the heating curve that's needed to heat that building, that's the one I ride all the way down to the bottom. Now, let's say I put baseboard in the building, and that baseboard needs a minimum water temperature of 100 degrees. I can't let my curve get down below that 100 degrees. So all of a sudden, the curve becomes something like this. So I'll have a slope, this heating curve may have a slope of 1.6, but I have to then reshape it to what you see here. And that may be a shift of 12 degrees, and we'll talk about slope and shift, and I may adjust the slope as well to give me that curve. Now, the thing is, when we start to look at making these adjustments, the one thing you'll hear people talk about with outdoor reset is something called constant circulation. And everybody will say that's your goal when you're doing outdoor reset. I select the right heating curve, and if that heating curve is truly the right one, I'm putting the right amount of heat here, the right amount of heat here, and the right amount of heat there. With that right amount of heat, the pump runs constantly, and as long as we stay within the turn down ratio of the boiler is balancing with it. Everything operates consistently, okay? But if I get above that curve, then all of a sudden, the heating system puts more energy into the building than is needed, so I need something to balance the room temperature, okay? So if I get in that minimum water temperature and I add this curve in right here, all of a sudden, I am not really doing constant circulation. I will have to have some sort of zone control. It's going to have to be thermostats. It's going to have to be either zone valves or zone pumps. Because here is constant circulation. Here is too much energy into the room, and that 70-degree temperature may all of a sudden creep up to 74, 75. So when I start to move away from the perfect curve, if you will, to something based on a minimum water temperature, typically my expectation is there has to be some level of zoning to bring comfort back in there. Zoning drives comfort. This minimum water temperature here drives comfort as well. But when somebody says, I'm doing outdoor reset, I'm thinking about constant circulation. Yeah, it is something that is nice to strive for, but it may not be something that you can achieve. Now, from a building standpoint, actually I had to go back for this because I put in the wrong slide, okay? When I do something like this, I do have to define it. If I look at a commercial buildings, usually the details where they'll have the operating characteristics of it. So I am going to have a water heating reset schedule. And in this reset schedule, this is where I define this point here and that point there. So whoever is setting up the control knows how to set that control up. And the definition is going to be based on, I'll define it by water temperature and space temperature. I should say outside temperature. So on a 0 degree day, I need 180 degree water. So that goes in my reheat schedule that shows up in my documentation for the project here on this chart. And then the other end is 68 degrees with 100 degree water temperature, 68 and 100. That way there, I've defined the two ends. So whoever's programming it, whether it's being done through the boiler control or the building management system, they know the two anchor points. But this is important when I move away from the constant circulation curve to something like this. I have to define either endpoint in order for somebody to be able to program it. And it's going to show up in a heating schedule like this, defining the 2 points. So I'm going to come back to the other question. Does every building need zoning? Now that we've kind of worked our way through a lot of discussion about outdoor reset, because when you talk outdoor reset, everybody always will say, we're doing outdoor reset. You're talking about constant circulation, aren't you? My answer always is not necessarily. And in my experience, it's very difficult to give constant room temperature with the way we build buildings nowadays in North America without zoning. Because if you look at something like this, there's a lot of different needs and a lot of different potential temperatures needed throughout this building. And I'm talking about from a space standpoint. Okay? So when I look at that building, I always talk about, you look at what's going on. Are there internal or external gains? I have this open kitchen area all the way across. Like a lot of people, Sunday, my wife was making a ham for Easter. The heating was turned off, yet when the oven went off, the temperature in the room in our house was running about 73 degrees. So that's an internal gain. You might have external gains through the windows. It could be about their lifestyles. Do they want to adjust the temperature? Is this bedroom not a bedroom, but set up as an exercise room where they want to run it down to the lower temperature because, you tend to have the exercise set a little bit lower. It's about the occupants. Are they young? Are they old? Are they somewhere in the middle? The style of the heat emitters. Is there any variation in the construction throughout the building? Flat out, did we put in the wrong heating curve? Or even with the wrong heating curve, it's from an aspect of setup, was there enough time built into the budget for the project to adequately set up the heating curve? Or are we trying to get out there early, quick in, quick out? So a lot of times it's the heating curve is your best estimate rather than dialing it in. But for a lot of reasons, all of a sudden I look at a building like this and I expect to see a mechanical room with something like this, multiple heating zones. That heating zones allow me to put in the heating curve, and here I'm doing it with a mixing valve. So here's my mixing valve. Here's a temperature sensor measuring the temperature downstream of the mixing valve. Here's my outdoor sensor. So that outdoor sensor is always key. I need to measure the outside temperature to do outdoor reset. I'm going to either measure the temperature here with the mixing valve. It may be a strap-on sensor after my low-loss header. It could be a sensor inside the low-loss header, or depending on what kind of boiler I'm using, it may be the temperature out of the boiler. But I need to compare the temperatures, provide that temperature here, and then because of any variations from that previous slide, I'll have my zone controls there for this one here, my six separate zones, that I can meet the requirements of that building and maintain comfort. You know, this way here, you know, I have my sensor in the room, the thermostat, and I run binary here. I run outdoor reset here. And what happens is, in most cases, I run near constant. You know, 85, 90, 95% of the time, the water is flowing through the heat emitters because I'm pretty close. And then this is just, the zoning is just there to fine tune the different areas of the building. Okay. Now, when I set it up, there's really 3 different settings that we look at: slope, shift, and room temperature. And it's all about how we approach the setting up of the heating curve and how we're going to heat that building. So we talked about slope, and slope are these numbers along here. You know, slope, you'll hear it referred to as reset ratio. You'll also hear it referred to as the heating curve. And you'll notice they all converge or anchor right here at the same point. So when I make a change in the slope, what it really is it's a proportional change. So on the 41-degree day, I proportionally change the water temperature moving up here in the same proportion that I do here on the colder days. So in the colder days, I get a bigger shift, a bigger movement in my water temperature going from one heating curve to the next than I do on the milder days. But what that does is, by having that proportional change happen, it's going to always keep it at 68 degrees, okay? So that's what happens when I make that adjustment. And this is usually the one that's called out to make the connection between the points, okay? On our control, we can also make a change in room temperature. What that room temperature does is, right here, that anchor point, I'm actually dragging the entire set of curves up here, because anchored in here, if this is the right curve, if the 2.0 is the right curve for my building, I'm putting out the right amount of water temperature to get to 68 degrees. There's no way to get that temperature any hotter because of that curve in the building. But if I make a room temperature adjustment from 68, say, to 72, everything moves over. And this is also a proportional move across, that I'm now still providing the right water temperature on the 50-degree day, on the 32-degree day, on the 5-degree day, to still drive a consistent, say, 72 or 74 where I put that temperature. So both slope and both room temperature are all about maintaining the room temperature through the full range of operation. Now, the other one's what's called a shift, and you'll hear referred to as a parallel shift as well. So what I'm doing is, I am actually moving up this line here a certain number of degrees. You know, I'm moving 5 degrees Fahrenheit, 7 degrees Fahrenheit. And what it does is it brings everything up. And what that does is, the curve doesn't move proportionally over the entire range. It moves the same amount. So if I move it 5 degrees here, I also get 5 degrees there, okay? But what that allows me to do is, if I've defined the heating curve as a point here and a point there, that shift allows me to pull the anchor point up to my mild day temperature. And then with the slope, I can take that slope and pull the slope, using the slope, pull it back to my design day temperature. Okay? And by having all of these three adjustments available, it really allows me to fine tune the heating curve for the conditions within that building. Whether it's about maintaining a consistent room temperature, or whether it's about maintaining a minimum water temperature because of limitations of heat emitters. Okay. Now, another thing that plays into this setup for the control, and this is where we start to get beyond just a single water temperature. You know, a lot of installations out there require multiple water temperatures throughout the building. You know, mixed heat emitters. Some radiant in a building, maybe an air handler, or some radiant and maybe some panel radiators. And what happens is, when I add extra temperatures, it's always going to be about adding mixing valves. This happens to show a non-condensing boiler with a 4-way mixing valve, okay? And over here, when I look at this mixing valve, because I want it to be in a location where the valve doesn't hunt, where I see good consistent temperature, when I compare the temperature going into the mixing valve to what's exiting the mixing valve, I want the boiler water temperature to be a minimum of 14 degrees warmer than what's going out to the system. And that's true whether I'm doing a 3 or a 4-way mixing valve. So from a standpoint of control, if this is the heating curve that's programmed into the control for this temperature here, all of a sudden this dotted line starts to play into the water temperature the boiler is putting out into the system, out here, okay? Now, it becomes more complicated when I add multiple mixing valves, because we'll see projects out there that have 2 mixing valves. Here's one mixing valve, call that system 2, the green line. We have a second mixing valve right here, that's the blue line. And when I look at the boiler supply or the common, what happens is the boiler has to compare these two and always maintain itself a minimum of 14 degrees hotter. Okay. Now I'm actually going to do this here. This is what I programmed. Let's call that curve there, that light line that I just added in there. Let's call that light line. That's the heating curve for the boiler. So I have so let's call this high temp, let's call that an air handler. Let's call this 2 temperatures of radiant, okay? So this line here represents where I want the boiler to run based on the requirements of that high temperature. But you'll notice right here, I get a crossover between the temperature that's going to the high temp versus the boiler supply to maintain the 2 mixing valves. And all of a sudden, my boiler curve now is actually here to there, okay? So when I start to add in mixing valves, and because of this delta T that exists, I have to keep the boiler always 14 degrees hotter, minimum. When I start to add mixing valves and I have a high temp, generally I look at it and say, this is one, whether you're thinking about it or not, the high temp really should have zone control, because if it doesn't, right here, right along here particularly, the temperature is going to be much higher than what's needed to support the outdoor reset on the building. And if I don't have that zone control in there, that part of the building will overheat. So again, when we start to look at outdoor reset, ideally everybody does want to have constant circulation, but because of a number of different factors, I always want to make sure that the consideration is there for zoning to ensure that we can tailor the room temperature to exactly what's needed to meet the demands of the building owner. So a couple of slides to tie us over, to kind of pull it together, to talk about some of the whys behind it. We talked a lot about the hows, but when we start to look at the whys, it's one of the things is with outdoor reset, it always is a discussion about comfort in the building. Because if I am putting the right water temperature in there, I maintain a good consistent temperature regardless of what's going on outside. So there is no swings of temperature inside the building. I have slow temperature changes. Also, if I can keep my zoning so that it's almost open 100% of the time, you don't see small variations. You think about it saying, the thermostat has a differential. If you've been in a building that's run constant circulation versus a building that is running off of zone control with a thermostat, you tend to feel much more comfortable a lot of times at a slightly lower temperature with that constant temperature and that constant heat output. And really the big thing is the building is playing keep up rather than catch up. It will make the adjustments, particularly when I'm going from a mild day into a cold day and not have to, catch up with the heat loss of the building because it's already on top of it. Okay. It's also about savings. If I lower my water temperature, everything runs more efficiently. My cycling losses are lower. My standby losses are lower. What's interesting from a commercial standpoint, particularly if I have a building that the heat is paid for by the landlord and not the tenants, when you do outdoor reset, all of a sudden open windows come out of the picture. I don't put enough heat in the building to heat the building with the windows wide open. So all of a sudden, whether it's a tenant or it's one of your kids opening the windows in the middle of the winter, that goes away because there's not enough energy to maintain 70 with the window open, okay? You know, something that plays in, and this is conventional boiler as well as condensing, we also gain from what's called the 3-to-1 rule. And what the 3-to-1 rule states is, for every 3 degrees Fahrenheit I drop the water temperature, my fuel consumption decreases by 1%. So if I have a system that's running at 180 degrees, and through outdoor reset I can drop the temperature down to 150, on the days it's running 150, that's a 30-degree difference. 30 divided by 3, that's a 10% savings. So when the water's 150 degrees, I'm running 10% more efficiently than the water's 180. And again, this is savings that's associated with all boilers, not just condensing boilers. And then finally, back to condensing boilers, the outdoor reset's going to make that condensing boiler more efficient. The lower the water temperature, the higher the efficiency. This is a chart that shows up. This is actually out of the ASHRAE manual. The bottom axis is inlet water temperature of the boiler, and over here it's about boiler efficiency. So I may go back to my building and saying, you know, I'm doing 180-degree water with a 20-degree drop. It's going in at 180, it's coming back at 160. On the design day, that's only about 86.5, maybe 87% efficient. But through outdoor reset, I can drop it down to 120-degree water temperature. All of a sudden, now that boiler is condensing and my efficiency is up to 90%. The lower the return water temperature, the higher the efficiency. So if I can get it down to 100 degrees, you know, there's 94. So, you know, I always throw that number in there because a lot of times people will say, I'm doing baseboard, I'm really not going to get good condensing boiler performance. If I can get that return water temperature down to 100 degrees, which most baseboard does support, with 100-degree return water temperature, I can get 94% efficiency out of that condensing boiler. And that's with baseboard that's designed for 180 on the design day. So doing outdoor reset, it's something that's easy to do. A few pieces of information are needed to set it up, but from a standpoint of comfort and savings, it's very beneficial to utilize it as a strategy for controlling the heat input to the building. Now with that, let's see if we got any questions. Miranda?
We do have one question, Jody.
Yep.
I am assuming the efficiency of the unit will go up with the outdoor reset. If the curve is off a little, won't the unit cycle more and get less efficiency?
Well, I guess it really, as far as the, I guess it depends on, you know, how far off of the curve you're going. But the answer is it will, if I come off of that curve, the unit will cycle more and I will lose efficiency in the process. But when we start to look at applications, and this is always, I'll call it a tough discussion. And from an aspect of projects, you know, there are always three separate things that are pulling at the project, and it becomes a matter of what one of the three are most important. You know, you have operating efficiency, you have comfort, you have installed cost. And, you know, when you start to look at something like, you know, doing a VITODENS 100 versus say a 200, all of a sudden the installed cost becomes, if the installed cost was probably more important, and because I've saved on the installed cost and I don't have all the full adjustability that I would with a VITODENS 200, then all of a sudden I've lost a little bit of the adjustability to push the efficiency up a little bit. But the thing is, I haven't sacrificed all the efficiency. It just may be that I can't achieve the maximum efficiency because I don't have that full adjustability. But the answer is yes. If I bring the bottom end of the curve up because of that heat emitter that I'm utilizing in the building, there is a sacrifice in efficiency versus running it all the way down to 68 degrees. But the important thing is you're keeping the customer comfortable and you are ultimately saving them money as well. And with that, is that our only one, Miranda?
That is the only one, Jody.
All right. Well, I want to thank you all for spending some of your time today with us. Certainly breaks it up for me working from home. And with that, I'm going to pass it over to Miranda.
Thank you, Jody. Just a few reminders before we head out. As stated in the beginning, a recorded version of this will be posted on the video library within the next week or two, so you will be able to go back and rewatch this webinar. If you requested the PDH credit, you will receive an electronic version via email in the next 5 business days. If you think of any additional questions after this, feel free to email me. We will be putting together a document with all the questions and the associated answers that will be sent out to everyone who attended today. And then lastly, if you're not aware, the Viessmann Academy does hold monthly webinars throughout the year. And then we also will be extending our COVID-19 rapid fire webinar sessions until May 17th. So keep an eye out for that. With that being said, that concludes our webinar today. Have a wonderful day and thank you for attending.